All right. Okay, it is 3:35, so let's get started. Okay, so our speaker today is Jessie Shelton. So a brief bio of Jessie is she did her undergrad at Princeton, and then she got her PhD at MIT in string theory. And then she did a postdoctoral position at Rutgers, where she transitioned from string theory to phenomenology. Then she moved to Yale and then Harvard, and then finally joined UIUC as a faculty member in 2014, and she has been there since. So Jessie, please take it away.
All right, thank you, Tova. It is my pleasure to tell you a little bit about some of the things I've been thinking about recently. So I'm going to tell you about displaced dark showers at the LHC. This is work largely with Simon Knappen and my student Dongshu. So the first thing you might wonder is why long-lived particles, although if you have been talking to Tova or Larry recently, you probably have some ideas about this already. But you might, if you're feeling very cynical, think that the answer is very obvious. There have been an awful lot of studies that have looked for promptly decaying particles at the LHC, and they haven't found anything. So it's time to turn over the next rock, and there's got to be new physics under one of these rocks somewhere. And to be completely honest, there's a little bit of truth in this, but the story is a little more sophisticated than this. And there are some good reasons why long-lived particles are very well motivated, theoretically, given what we have learned so far from the results of the LHCs to date. So for one thing, the fact that there have been more prompt analyses compared to the number of long-lived analyses is not just by counting a completely fair description of what we've learned from those different analyses so far. One prompt search is not exactly equal to one displaced search. They're sort of qualitatively different in a lot of ways, speaking very generally. The great power of long-lived particle searches is that, unlike a lot of prompt searches, the standard model background for these final states is intrinsically small. The LHC, of course, is a proton collider. Protons are composite particles. So you're smashing, composite particles together. They interact under, strong forces. They make a lot of, high background hadronic stuff. You don't have a lot of control over the initial final state, and there's a lot of noise to sift through for standard signatures. But if you look at this plot, this is showing you the expected rates that you can predict from standard model processes as a function of the displacement of a muon that you see in the final state. This quantity d naught here is the transverse impact parameter. So if you're looking down the detector, so this is a cross section. So this circle here is where the beam would be. This is a transverse plane. Here's a muon track, starts here, then you project this back. The transverse impact parameter is the distance of closest approach of the track is projected to the beam pipe. And so you can see here, as you increase the degree of displacement, the further away from the beam pipe this track appears, the background just drops. There is standard model background. So there are some species in the standard model that have an interestingly long lifetime. So taus, HF here stands for heavy flavor. So in particular, B quarks. So the biggest physics background here is B quarks. And then there's some error here shown in gray. And you can see, as you go out in displacement, the standard model background just drops exponentially fast. So looking out here, looking for new physics that predicts signals out in this big transverse displacement parameter, impact parameter bin here, you're going to do a lot better than looking for physics over here because the background is just intrinsically small. So these searches can be very powerful. One event, one new physics event out here tells you a lot more than one new physics event in here. For this reason, displaced searches can often be relatively insensitive to the properties of the particle that's decaying. So this was pointed out for jets quite some time ago by this group. This is where I took this figure from. They're showing one of the searches at the time that was looking for a displaced jet. The signal that the analysis looked for was for, two jets coming from a displaced point, and these groups showed that actually, the search is pretty sensitive to 3 jets too, because the reconstruction criteria are simpler. You don't have as much background, so you don't have to make as many precise requirements on the properties of the new physics that you're looking for. In other words, you can make more inclusive signatures. And that means that the searches that you can construct for long-lived particles are typically powerful and inclusive. And therefore, these searches can be very constraining and very general in ways that it's hard for the higher background prompt searches to be. Now, from the theoretical side, there are a lot of reasons to interpret the null results for prompt physics together with the discovery of the Higgs boson as a good motivation to look for displaced signals. So here are some very famous examples from the literature. If you look at the Higgs boson and you like to solve the hierarchy problem, you might be interested in seeing what this does to supersymmetry, which is still one of the easiest ways to resolve the fine-tuning problem in a way that doesn't involve bending over backwards with model building. If you have a fairly heavy Higgs mass, like the standard model Higgs mass likes to be, by heavy, I mean heavy compared to the Z mass. So the Higgs mass is substantially above the Z mass. And in order to get that to happen in supersymmetry, you need to have, the easiest way to do it is heavy supersymmetry breaking scales. That means your superpartners are also going to be heavy, and this can lead to long-lived particles in a variety of ways. One of them is called mini-split. The idea here is your superpartners of quarks, or squarks, are very heavy, way out of the kinematic reach of the LHC, but possibly the fermionic superpartners, like the gluino and the neutralino, are light enough to be produced. In that case, the only way the gluino can decay in these models is through an off-shell extremely heavy squark. And so the ratio of this mass scale is large, and that can, so the scale in the denominator is large, the scale in the numerator is a lot smaller, and that can make the rate for this decay to happen interestingly small. Another SUSY breaking scenario has at the bottom of the spectrum a gravitino, which is, you can think about as a particle that gets all of its mass from supersymmetry breaking. So the mass of the gravitino, as well as its couplings to matter, is controlled by the scale of supersymmetry breaking. The higher the SUSY breaking scale, the more weakly this particle couples. And so this coupling becomes, again, interestingly small. On the other hand, maybe you think not seeing SUSY so far is a good indication that there is no SUSY to be found. And if you're interested in other ways to cure the hierarchy problem, you can try something called so-called neutral naturalness, where the partner states of the standard model that are responsible for fixing up the quadratic divergence problems with the Higgs mass, also known as the hierarchy problem, are, instead of being charged under standard model interactions, in particular the standard model strong force that would mediate the copious production of these states of the LHC, take that away, make them charged under a mirror reflection of the standard model color force instead. And you get these theories called neutral naturalness. This predicts a mirror copy, in some models, a warped mirror copy of the standard model that talks to the standard model only via the Higgs boson. So the Higgs boson is the only state that talks back and forth. In that case, the leading signals of new physics at the Large Hadron Collider are Higgs decays into new particles. These new particles are composite states. They decay via higher dimension operators, so there's a mass scale suppression that comes in again, as well as potentially small Higgs mixing, and this pushes you to long lifetimes again. Cosmology also points to other reasons for long-lived particles. So now this doesn't necessarily have anything to do with LHC results, except insofar as cosmology still likes to point to electroweak scales as possible places for new physics to show up. One thing we know about cosmology is that our universe has a very small preference for matter over antimatter. That is why we're all still here and not just dissolute clouds of photons to travel the featureless wastes. if you believe in supersymmetry, then you can give the superpartners of quarks a baryon number violating coupling to pairs of quarks. So this takes something with baryon number 1/3 and turns it into a state with baryon number 2/3. This kind of coupling would, if it were big in the early universe, take any baryon number asymmetry and a preference for protons over antiprotons and get rid of it. So if you want to have supersymmetry and baryon number violation through these couplings, then you have to, in order to explain our existence, have these particles very small. And then you get a macroscopic lifetime for them if you produce them at colliders. Or if you want dark matter model building, this is a box. You can open it up and pull various long-lived particle mechanisms out left and right. Here's just two. One of them is so-called freeze-in of dark matter, where you've got some particle in the hot thermal plasma, including the standard model that was there in the early universe, that has a very tiny coupling to dark matter, so that every now and then it pops out a dark matter particle in the very early universe. Then very gradually over time, this dark matter abundance gradually accretes until you have the observed relic abundance now. This coupling has to be very small, just in order to reproduce the observed amount of dark matter that we see. Therefore, again, a macroscopic lifetime for this particle if you produce it at the LH state. And then another thing you can do is have dark matter interact with another particle X in a process called co-annihilation, so that dark matter can interact with this other particle in such a way that that interaction controls the amount of dark matter left in the universe at the end of the day. So you can think about this as dark matter sort of co-freezing out with this particular particle X. To make this work, these particles have to be leaving thermal equilibrium at about the same time in the early universe, which means they have to be very close in mass. That means their phase space is very close together. That phase space suppression, the fact that there's just a teeny kinematic window for X to decay into dark matter equals something else. In this case, is what's responsible for making the lifetime long. So summarizing, there are a variety of reasons, mechanisms that can give you long lifetimes for a new particle. You can have hierarchies of scales where some ratio of mass scales enters the matrix element describing the decay, and that makes things the lifetime, the decay small, the lifetime long. Restricted phase space does the same thing. And sometimes you just flat out have dimensionless tiny couplings. These are often forced to be small because when it's zero, you have a restored symmetry. So here are some examples. These things are suppressed by hierarchies of scales. This is phase space. This RPV coupling is an example of a flat out tiny coupling. So these are natural and frequent ingredients in beyond the standard model theories, famous examples. There are also many very familiar examples in the standard model itself, and I'll say a few words about that in a bit. So right now is a very interesting time and an exciting time to be looking for long-lived particles, because there's been a lot of development, especially on the experimental front, that's sort of pushing forward this interesting stuff that we know about long-lived particles at the LHC in a variety of dimensions. So looking at broadening the ranges of lifetimes that can be probed, looking at broadening the kinds of final state energies for which we can study long-lived particles, and also broadening the numbers of displaced objects that we can look for in the final states. So the limiting factor in a lot of long-lived particle analyses is often making sure that you record the event on tape in the first place, because these are not the kinds of signatures that detectors were sort of first designed to find at the LHC. And so a lot of the hardwired triggers are not easily able to record patterns that look very different from the patterns that were put in at the beginning. And this is something that you should never trust theorists to tell you about triggers. You should talk to your experts that you have in-house. But new triggers can be important both for broadening the range of event-centered mass energies, particular, pushing them down to lower center of mass energies where the standard model backgrounds are higher, particularly at the trigger level. Also in terms of broadening the range of lifetimes that you can probe on both the short end, on both the short end and on the long end. And other things that are interesting here are interfaces. Sorry, let me go on. Okay, so here's an example of a new trigger. Recently, this is a preliminary result from CMS that came out this summer. They have a fancy thing called data scouting that reads out limited information in events that have very low mass dimuon pairs, which lets them go down to very low masses compared to what other kinds of analyses can probe. And this also lets them look at long-lived searches where the particle that's decaying into pairs of muons travels some macroscopic distance before it decays. So you can see here, these results are shown for C tau of 10 millimeters, importantly not zero. Okay.
That graph?
Yes.
What are the vertical gray bars?
Oh yeah, so those are regions where you have a lot of background from Quarkonia that in this preliminary version they have not modeled. So here you have some mesons that can easily decay to muon pairs that can give you backgrounds that are harder to estimate. Yeah, good question. There are some proposals for dedicated long-lived particle detectors. I've put here 3 that are some of the earliest. There are others. This is something called phaser. It sits very far forward. This one is actually in there taking data. This is one called Codex B that is planned to function sort of like an auxiliary add-on for the LHCb detector. So here is LHCb and here's Codex B is the idea. And this thing is Methuselah, where the idea is, here's one of the main detectors. This has now been settled to CMS. And then you make something long-lived in the collision and it travels through, because it's neutral and doesn't interact easily, through all of the rock and goes off in a surface detector here. So all of these have the idea that you make something in the beam and then you have like a big shield to stop background and you wait for something to travel a big distance away and decay in an instrumented volume. So the idea with these things is it gets around the trigger restriction because the only signals are going to be things that make it through all this stuff. The other thing is it gets you further away from the interaction point, and so it can push out the lifetime axis as well. And now something that I've been quite interested in is the expansion in the number of particles that you're making. It's often easiest and natural to start with 2. If one of these things is low background, 2 is ultra low background, and that is awesome, especially as the luminosity goes up and things that used to be ultra low background are now just low background. The flip side of there not being a lot of standard model background is that the backgrounds you do have are often instrumental and very, very hard to predict from first principles. And so understanding what the backgrounds are as soon as they start getting to levels that you have to grapple with is a headache. And so pushing down to single displaced object searches, while this is very important, especially when you're starting to push the long lifetime regime or in theories where you don't pair produce these. This is very important. It's also hard because often you have to deal with background rejection here at a non-trivial level. Something else that's very interesting to me is instead of just 1 or 2, what if you have an event that makes a lot of these? And this is the area where I think right now, theorists have the biggest chance to do something really useful because understanding how to grapple with the theoretical uncertainties in a lot of these models that make multiple displaced objects in a way that lets us get the most out of the possibly very powerful searches we could do for these models is an area of real opportunity for the LHC. So there are already some analyses going in this direction. The idea of both of these analyses is you start with standard model stuff, and then you produce something that is charged under an interaction of force, but not a standard model force, a hidden or dark force. And so it undergoes some non-trivial evolution, just dark states interacting with other dark states, making a very complicated cascade in the dark sector. And then some of those states will be unstable and come back to the standard model. There have been a couple searches, one with pair-produced objects along with standard model jets, and one for so-called semi-visible jets. I'll talk about that in a sec. So confining dark sectors are what I'm talking about when I talk about these dark shower models. So historically, there have been very strong motivations for long-lived particles from perturbative theories, in particular from supersymmetry. And a lot of the famous examples I talked about at the beginning are from perturbative theories. These are weakly coupled theories with a few states. But long-lived particles are even more generic and even easier to realize in confining theories. The majority of the long-lived particles in the standard model are hadrons, so particles made out of quarks and gluons that are interacting under the confining strong interaction in the standard model. So the neutron is very long-lived because it's so close in mass to the proton. This is an example of small phase space, which is guaranteed by an approximate symmetry, the standard model isospin symmetry. The K long is forced to decay through a small CP violating coupling to a 3-pion final state. B meson, long-lived because of an approximate flavor symmetry. That means it's coupling to through the W boson to charm strange is just small because V VB S is small, and then similarly the D meson. So there are two main reasons why long lifetimes are so generic. Thing one, you're dealing with the decays of composite states. Composite states decay through high mass dimension operators. They're not elementary states. So when you write down the field that describes their lifetime, you have to write down these additional mass factors. These are almost always small. How small depends on your theory. We'll have some examples. The other reason is you have accidental global symmetries, and these are generic in confining gauge theories. They could be discrete symmetries like CP, K long. They can be approximate flavor symmetries, even like the standard model pions. There's an approximate isospin symmetry. The neutral pion can decay because it has zero net isospin. It can decay through the dimension 5 operator to pairs of standard model photons. So the dimension 5 is a loop operator. So there's a small factor. M pi over F pi is less than 1, but in the limit that the isospin symmetry was exact, this would, let me put a pin in that. However, the charged pions do carry isospin, and that means that they are forced to decay through the isospin violating decay here with the off-shell W boson. Now the W is much heavier than the pion mass, so you get this ratio of small mass, the small ratio of mass scales here. M pi is 140 MeV, W boson is 80 GeV. So this is a small ratio, and it shows up squared. So this approximate isospin symmetry is part of why charged pions are much longer lived than neutral pions. All right, so let me talk about dark showers. So it turns out that dark showers seem to be a design trend. I'm not talking about that, although that might be what you think about. I am talking about the characteristic signature that you get when you have events that have particles that are charged under their own, sometimes you'll hear hidden, sometimes you'll hear dark. It means the same thing. It just means not the standard model interactions. It's a force that the standard model particles don't feel. So they have confining interactions, meaning interactions that get stronger as you go lower in energies. This is very much like QCD, and so these signatures have a lot in common with QCD jets. So you start out with, you produce something like, think about it like a dark quark, and then it can emit a dark gluon, and keep going. Dark gluons can split into dark quarks, or they can split into more gluons. And so you start out with a relatively high energy dark quark. And so you can calculate in perturbation theory what the probability is to spit off a dark gluon. But every time you spit something off, the particle at that splitting becomes lower energy. And so as you go on, you have more and more chance to make more and more of these things. And eventually you end up with a whole bunch of very low energy things that are fairly strongly interacting at that point, and you undergo a complicated non-perturbative process at the output of which you have these bound hadrons as your good degrees of freedom. So you can split up in these theories the evolution inside the hidden sector into two pieces. There's a parton shower-like piece that you can describe reasonably well using perturbation theory. So, you know, I don't say that I like doing these calculations. They can be tedious. If I like doing these calculations, I wouldn't specialize in BSM physics. I'd be doing precision QCD. There are people who do precision QCD. There's some very pretty stuff in there. I'm doing BSM physics. The hadronization part, on the other hand, is non-perturbative. This is not something that we can calculate from first principles. We know an awful lot about what the spectrum of possible final states can be. In a lot of theories, you can, well, in the standard model, you can learn a lot about the spectrum of the standard model from lattice QCD. There are a limited set of other theories that are fairly close to QCD, for which we know a lot about the spectrum of low-lying hadron states. What we cannot calculate from first principles is, with any known technology yet, is the dynamic process of hadronization. In other words, I couldn't tell you from first principles, if I start out with a 30 GeV PT quark, how many pions I'm going to make. We have good descriptions of this for standard model QCD because we have had decades to build phenomenological models and match them to experiment. So this part of the dynamics, we have excellent theoretical control over. This part we don't, and it's important to remember that. So there's some characteristic features of dark shower events. For one thing, and these are all things that make them different from other kinds of signatures. So for one thing, you're making a variable and potentially large object multiplicity. It has non-standard model-like distributions of both energy and flavor. The final states you're making are often non-isolated, and so they will not necessarily be isolated from prompt stuff, and they may not be isolated from each other. And you typically have a hierarchy of lifetimes for the particles in these events, same way that the standard model hadrons have a hierarchy of lifetimes among themselves. So that means detector scale lifetimes for at least one of the species you're making are generic. Not universal necessarily, but they're generic. So some examples people have talked about are so-called semi-visible jets, where you have basically two possibilities. You have things that decay promptly or things that are detector stable. The models that people have made are QCD-like, they're jetty events, but an order one fraction of the particles in the jet escape the detector and so appear as missing energy. They've made a model with a dark vector boson, a Z prime that mediates the production. It's a heavy Z prime. It can decay into both standard model stuff, which is how you couple it to the standard model, and it can also decay into these dark quarks. Another example that people have searched for are so-called emerging jets, where the shortest lifetime species already has a macroscopic lifetime. So you make a jet of these things, or again, jetty events, and then you make a bunch of particles that have a finite lifetime. And so these things start decaying and appearing in your detector one at a time as the jet evolves. The specific model that people have realized and looked for involves a pair production of quarks that carry both standard model charge as well as dark color charge. And so they decay into a standard model jet, standard model jet, and then a dark emerging jet. So because these do carry color charge, that means because the way that you produce these things involves pair production of colored particles, we have pretty good constraints on pair production of colored fermions, and so the mass scale for these things tends to be pretty high. But in general, you expect some combination of prompt stuff, displaced stuff, and detector stable stuff, because you expect a hierarchy of lifetimes. That means your detector signal, what you see in your detector, what the final state looks like when you go look for it, is inextricably tied to the multiplicity of a specific given dark hadron species. You'll have some species that decay as displaced. You need to know how many of those do I have, which means you depend on things that we can't calculate from first principles. Okay, the only place we can make firm statements about this particular quantity is in QCD, where we have the benefit of decades of measurements. For any BSM model, we're basically making it up. So we have to do that in order to provide a model, the reference model that we can use to guide the search. But you need to bear in mind, we cannot get around the fact that these predictions are not infrared collinear safe predictions. To make things worse, the existence of these jetty-like events is an expectation that's inherited from QCD. QCD is a kind of confining theory where you can start out with a phase of perturbative evolution, which tends to favor these relatively narrowly collimated sprays of energies. QCD has this nice separation between this perturbative part and this hadronization part. This is not necessarily a universal feature of dark confining gauge groups. QCD is what's called a small 't-Hooft coupling gauge theory. There are gauge theories for which you cannot ever write down such a perturbative phase that would give you a parton shower. You can't separate the parton shower from the hadronization. In the opposite limit from QCD, it's at very large 't-Hooft coupling. You expect, instead of these narrowly pencil-like jetty events, you expect spherical events instead. Famous papers by Hoffman and Maldacena, developed phenomenologically by these authors. So we can have some control about the QCD-like limit, the very spherical limit. In the middle, no good tools. There are some toy models. So you have to bear in mind the class of theories that we expect exists. We know that we don't know how to describe the energy flow in part of this theory, in part of this theory space. So given how hard it is to make predictions, I think the best way to go forward is to do some inclusive searches and be very aware of the places where the tools that we have are relying on things that are extremely hard to calculate. In other words, do the best you can in making choices for your search program that render you as insensitive as possible to variations in the model space, and be aware that when you're using tools in parts of parameter space, they're necessarily going to be toy models because we don't have the technology to do any better. So to flesh that out, when I say, so different people sometimes mean different things when they talk about dark showers. What I mean specifically for the rest of this talk, when I talk about displaced dark showers, I mean signatures that have more than three, at least three displaced objects per event. Partly because if I only have two, well, there's already a big class of searches that are looking for 2 displaced objects per event. So I'm interested in building the high multiplicity end of this search program. Now, the more displaced objects I have, the cleaner the signature is, because again, displaced objects are low background. The more of them I have, the lower background I have, which means hopefully, if I have a search strategy that is looking for more of these objects, I can get away with being very inclusive. I don't have to make a lot of requirements on what else is going on in the event. And so even if I don't know a lot about the theoretical description of how energy is going to flow in the event, if, for instance, if I'm interested in one of these intermediate shower where we don't have solid theoretical description for the energy flow, as long as I am making very minimal requirements on the distribution of these objects in the event, then we're basically doing the best we can. These are very inclusive searches. We do them at a very low background. And so if you report cleanly what you have, you cast a broad net, and then no matter what is out there, you're doing the best that you can. That's the idea. So Practically, we're going to use QCD-like benchmarks with these sort of these jetty-like things. Try to prioritize inclusivity at the analysis level. Of course, there's going to be practical limitations. So this is prioritize, not insist on. And then ultimately, down the road, come up, add some toy models and just see how good you do. So there are parts of this evolution that we know well. So a dark shower will involve some part that involves, producing these things from standard model initial states. Then the complicated evolution within the hidden sector, which is, where the theoretical challenges enter. And then the decay. The parts of this evolution that involve talking to the standard model, we have relatively more control over. So we'll try to leverage those to be as smart as possible to maximize our sensitivity to this mess in the middle. So production. My opinion is, it is a good idea to keep in mind as a motivating case, production in exotic decays of the standard model Higgs boson. One reason is, this is minimal insofar as I don't have to introduce another particle to do the job. I'm just going to use one that I already have. For another, the Higgs is relatively low mass. The Higgs is 125 GeV. Center mass at the LHC is 14 TeV. So that means the Higgs is sitting in a regime where you're typically fairly high background, which makes it a challenging benchmark for trigger and analysis development. I know that's hard. Part of the reason why I think it's worth asking very clever people to work very hard to figure out how to do this is because the more sensitivity you can retain to relatively soft, long-lived particles, the better you can do it, increasing your overall acceptance and therefore making your searches more inclusive, which helps to mitigate all these theoretical uncertainties about multiplicities, about event shape. The more you can catch, the better you can do at being inclusive.
What is a soft long-lived particle?
Good. It's one that's produced with relatively low transverse momentum, so it doesn't have a lot of energy. Good question. Thank you for asking. The other advantage about working with the Higgs boson, although it's hard here, is if you invest a lot of time in it, you can always guarantee there's a built-in triggering fallback through the associated production with leptonic decays here. But if you don't like that, we also have some ideas for how you can produce it through a heavy mediator, which lets you broaden the scope of your searches at the cost of making your your model parameter space bigger. Okay. So for the showering and hadronization, we're using existing tools. So in particular, we use the Pythia 8 Hidden Valley module. Pythia 8 Hidden Valley is set up to let you run QCD, so meaning 3 colors, an SU3 gauge theory, with n flavors of quarks. And we, in our paper, adopted NF equals 1. I can talk about the reasons for that choice more offline if anyone is interested. So it has QCD-like parton shower evolution. That part is, again, under good theoretical control. And it has a QCD-informed hadronization model. What the Hidden Valley module contains is a stripped down hadron sector. It consists of spin 1 mesons and spin 0 mesons. For familiar 2 light flavor case, these would be rho mesons and pi mesons. We're doing 1 flavor, so that means we have sort of the analog of the omega in the standard model and the analog of the eta. We put tildes on them to remind you that we're not talking about standard model particles, but the hidden sectors. This NF equals 1 theory has no Goldstone bosons, which means, so unlike in standard model where the pions are sort of unusually light compared to the other hadrons, here all the hadrons have sort of natural mass scale of order the scale at which the hidden theory becomes strong and starts to bind things. You can think of this as the characteristic binding energy in the mesons. Then, so we have basically 2 mesons, a spin 1 and a spin 0, and we basically dial the mass parameter of the spin 1 meson relative to the spin 0 meson to control whether or not the spin 1 can decay into pairs of the spin 0 or not. I want to emphasize, this is a toy model. I do not feel apologetic about this because, again, any non-standard model theory we do not have good control over the step of hadronization, so we might as well just own that and take a signature-based approach. Okay, but the decay portal, so we can, again, this is how things talk to the standard model, and so we have more understanding of what's going on here. Our paper, we wrote down we wrote down a discrete set of choices, 5 choices. We had some guiding philosophy in mind to write down this particular set of decay modes. We were concentrating on low operator dimension because those are the ones that will decay back the fastest. The higher operator dimension, the more powers of mass scales are involved and the longer the decay. So if you're interested in things that decay inside the detector, you want lower dimensions. These are also the things that are likely to happen the fastest if they're there at all. We didn't want to deal with flavor model building, so we restricted to theories that did not include any beyond the standard model sources of flavor violation. Those 2 philosophies gave us the first 4 and then stop. Then we added one where we put in a operator that's in very close analogy to the standard model pion decay. So together, these operators give rise to a wide range of phenomenological signatures. You have decays to gluons, basically, which gives you a hadron-rich, more tracks, lots of hadrons. This one gives you basically photons and nothing but photons, so it's a photon shower. This one will give you very typically a semi-visible jet. It's very hard in this model to get rid of the missing energy. It will always give you missing energy. These other ones have choices to give you missing energy or not. It will also weight you with leptons more. This one will decay through the Higgs portal, so it will tend to favor heavy flavor. And then this one decays like the dark photon branching ratio, so it'll give you a lot of leptons, and then as you get heavier, it will give you hadrons. Part of the point is, I may not know exactly how many of these etas or omegas I'm making. Sorry, this should be an eta. But if I have this operator, then I know exactly as a function of mass of this guy, what the branching ratios are and what the lifetime is going to be. So light dark mesons are generically long-lived. And again, they're composite operators. You also have to be careful about how easy it is to construct the operators in the first place. So here's an example. If I want to couple my composite eta meson to pairs of gluons, well, this is a dimension 5 operator, so it goes like 1 on a mass scale. Now I want to figure out what is this mass scale. Okay, how would I make this operator? Well, my eta is really a bound state of a quark and anti-quark. So this is dimension 3. So I better add some dimensions here. This is the natural dimensions at the confinement scale. Then I can build this coupling by having a loop of heavy, beyond the standard model charged fermions that also talk to this pseudoscalar that then talks to my dark quarks. So I get from this propagator a heavy mass scale from this particle. This loop gives me a 1 on mass for the mass of these heavy guys. So put that together and I get this idea for what my scale should look like. But these are colored BSM fermions. They can't be too light. So I therefore have some limits on how big I expect this scale should be, and therefore what this lifetime should be in terms of what I estimate for how heavy this thing is. Note the steepness of this mass dependence. That's again because this is a composite particle. And then the dependence on this mediator here. So I'm running low on time. So you can do similar exercises for all the portals and you can come up with some estimates. So you don't want to say, these are not hard lower bounds. These are guides to understand where you can easily construct models that work. So it's a guide to understand where high multiplicity signatures are the most interesting. And it depends, again, very steeply on the mass of the visibly decaying particle. The particle is giving you your long-lived signature. It matters because if I have a minimum C tau that's like, more than kilometer scale, it's not going to decay in the detector. If you make like 300 of them, who cares? So if you want a high multiplicity signature, right, and you want to decay through the photon portal, maybe you better be at heavier masses. That's how to interpret this. And again, these are not hard lower bounds. They're a guide for working with reasonably well-motivated models. So here are some plots that show you roughly how the multiplicity per event scales as a function of the visibly decaying particle mass. This is for the gluon portal. We've got a couple, so these curves are showing the plus minus 1 sigma band. Remember, we have a variable event multiplicity, a variable particle multiplicity in an event. This is for our high multiplicity benchmark, where if you make omegas, they decay to pairs of etas, and then the eta is the thing that's showing up as an interesting thing in your detector. Here, we've shut off that decay, so the omegas can't decay, they're stable, they just go out the detector. Okay. That's why this is lower. So solid here means decays within 1 meter. Dashed means effectively prompt. And so this is assuming the minimum lifetime. It's always easy to make things higher. Okay. So this says if you want to do something where you produce this thing at 125 GeV, so in the Higgs boson, you want a high multiplicity shower, then you shouldn't be doing this below 5 GeV. And you probably want this benchmark and not this one. On the other hand, so Higgs portal is qualitatively similar. The reason why the Higgs portal is worse is because so Higgs compared to gluon portal, in this regime, it's fighting the small Yukawa couplings, whereas this is fun and games with confinement. All right. And then vector portal only makes sense because here the visibly decaying particle is the omega rather than the eta meson. And so this one only really makes sense in the case where they are nearly degenerate. And that then tends to give you relatively low multiplicities if you're doing things through the standard model Higgs. But if you use a heavier mediator, so apologies for abuse of notation, here H is heavy, here H is Higgs, here H is heavy. So in this particular benchmark, if you you can get high multiplicity here. If by high multiplicity, you mean a reasonable fraction of events with at least 3 objects. But if you want a lot, then you should use a heavier mediator. All right, so let me summarize. Long-lived particle searches are one of the major outstanding discovery opportunities at the LHC. One of the things we have learned from previous null results is if new physics is accessible at the Large Hadron Collider, it is likely relatively weakly coupled to us and or takes an unusual form. And so long-lived particle searches are naturally motivated in that way from a lot of different directions. You can use this kind of setup to address a lot of the fundamental mysteries of the standard model, including the hierarchy problem, including dark matter. And there has been less model building to do these with confining and or multi-component hidden sectors than with perturbative hidden sectors, but that's honestly mostly because it is harder to work with confining gauge interactions, not because they're less motivated. The signatures are complicated and high multiplicity, but they are indeed a well-motivated generic possibility for beyond the standard model physics. The one example of a self-interacting set of particles that we have, also known as the standard model, contains a confining hidden sector, also known as QCD. There are, unfortunately, intrinsically enormous theoretical uncertainties, which mean that we have to think carefully about how to develop a systematic inclusive search strategy for the clean signatures that are predicted in such a way to make sure that the results are useful in a legacy sense, so easily interpretable and maximally insensitive to the necessarily toy models that will be employed at various steps. Related with that, and this is subject of ongoing discussions, I'm happy to summarize for anyone who's interested, we need to clearly understand the current Monte Carlo tools. Honestly, before we started this project, I thought the Pythia Hidden Valley module did more than I realized that it did. The hadronization sector of the Pythia Hidden Valley model is a little opaque, and we need to understand what it's doing. It's also important for experimentalists interested in running it to know that Pythia Hidden Valley is different in a lot of ways from Pythia QCD. And it is important to understand what it's doing when you're using it. And I think one interesting thing to keep an eye on if you're interested in this area is evolution in the Monte Carlo tools in this area. All right, thank you very much for your attention.
Thank you. Okay, let's have questions. Let's start with the students.
In the plots at the end, when you're showing the multiplicity of the different decay sectors, what are the dashed lines?
Good. So this shows where where things become prompt. So this is where minimum lifetime means. So these are decays within 1 meter. This is decays within, I forget exactly what our cutoff was for prompt, something like 1 millimeter probably. Yeah, honestly, I forget exactly what that cutoff was. But the idea is here, you have no trouble with the minimum theoretically estimated lifetime, this lifetime here, you have no trouble making so many prompt events. So you can see here, here the putting in the minimum lifetime is going to give you some things that are still displaced and then some things that are that count as prompt.
So you're basically saying that down at the bottom, like the lower x-axis end of this plot, this is where it would make sense to do an emerging jet search as opposed to a semi-visible jet search maybe later on, or looking explicitly for.
Good. So I want to emphasize that you can always get a longer lifetime. That's easy. It's hard to get a shorter lifetime than these curves, but you can always get a longer one. So for instance, here, if you want a longer lifetime, oh, that's easy, push this up.
Gotcha.
Yeah.
Other questions from students?
Why can't color charged beyond standard model fermions be light? You sort of offhand said they can't be light.
Good. Standard model color charge, yeah. It's basically because they're easy to make. They have to decay to something standard model that carries color charge.
Okay.
And that means you're making large cross sections of something that goes to jets. That is a signature that people looked for very hard in the first runs of the LHC, because it's one of the bigger things that would hit you in the face when you turn it on. And unfortunately, we didn't find anything. So that means these things have to be heavy enough that you can't make them in large quantities at the LHC.
Great.
Great. Other questions more generally?
What is a good degree of freedom? That was, you mentioned that on one of your slides.
Okay, so the question is, what counts as a particle? So at high energies, the things that are like the things that behave like particles, so things that carry the energy, travel for a distance before interacting, the things that are close to the eigenstates of your system. At high energies in a confining gauge theory, they're so-called partons, like quarks and gluons. But at low energies, quarks and gluons don't travel macroscopic distances. They aren't in any sense the meaningful eigenstates of the system. The quantities that act like particles that travel, interact, those are hadrons, composite states, pions, rhos, protons. So when I say good degrees of freedom, I mean the things that look like particles. Up here, the things that look like particles, as we understand them, are quarks and gluons. Down here, there are hadrons.
Okay, can you give me a sense of why that would be called a degree of freedom?
Good. Degrees of freedom is physics speak for the stuff in my system.
Okay, okay.
Very technical definition here.
All right,
I-
thank
I-
you.
I have a
Go ahead.
question. Yeah. Thanks for the great talk, by the way. I'm just wondering, thinking about these confining theories overall, and so you mentioned the range of possible Toft couplings giving rise to jetty versus non-jetty states and this kind of thing. And I'm wondering, is there any link between the size of that Toft coupling and like the possible lifetime ranges, or are these completely separate?
Yeah, that's a really good question. So the arguments that we know how to make most easily are about theories that are more QCD-like, so small anomalous dimensions. And so certainly all the lifetime estimates that we've made are small anomalous dimensions. So thing is, if you really have a conformal theory, so infinitely larger Toft coupling, then you can't get decays. If you couple to the standard model enough to get the decays, you have to basically break the gauge symmetry enough to eventually you'll evolve, and then you'll leave and make the particles then decay. So as soon as you get to that leaving step, basically you are getting to a regime where you can put in your you have to gap the spectrum. That gapped spectrum regime, you can revert to the standard small anomalous dimension expectations for lifetimes. That argument took us months to believe. And it can still be hammered out a bit more, I think. Yeah. It's a really good question.
That is, I'm curious about a little more detail on that, which would probably take me a bit to understand. Is there any like good resource for, is that written down anywhere?
No. Hopefully that'll show up in some future work. If you're interested in this, you might look at, so Matt Strassler has a paper called Why Unparticle Physics Are Examples of Hidden Values that talk about, so unparticle physics is briefly trendy language for a nearly conformal gauge theory. And Matt has some comments about what you can expect about how you have to gap that. A lot of that work is sort of obviously part of a dialogue at the time, but it is the closest I know to something that talks about this in sort of non-formal, that talks about it in a way that usefully makes connection between the relatively formal field theory of the near conformal evolution and then the more phenomenological, okay, yes, but what does this look like practically? Yeah, that's where I'd start. Yeah.
Great, thank you. Other questions from the room? I guess one kind of practical question I would have is, as experimentalists, right, we always want to sort of have some idea of a cross section so we can figure out which masses might make sense for us to focus on. And I know that in the soup search that we're working on here, we have some cross sections that I believe. And I honestly don't know anything about like what exactly how they're assumed or why. Do you think, how much space do you think is available? Like, is there infinite space of what those cross sections could be? Are there preferred ideas? Like, what would go into making that determination?
So I'm going to tell you stuff about what I worked out in this paper, partly because that's what I'm confident about saying, because it can get model dependent. So one reason to like working on stuff produced in the decay of the Higgs is because that gives you something fairly concrete for production. You have a fixed production cross section, you can dial the branching fraction, but you're bounded from above by observations. However, so as I mentioned when I talked about the production modes, I went too far, sorry. So when I talked about the production modes here, so we made some benchmarks. And we also put in some ideas for alternatives to the Higgs production, some so any of the decay portals are essentially telling you, look, you have some idea for some state you're integrating out that connects your hidden sector partons to the standard model, because that's where you get that decay portal from ultimately. So we have some UV completions of those operators that involve BSM mediators. Then you can relate the S-channel production through that mediator that you would expect for a given mediator mass and a given mediator coupling to the standard model. That is correlated with the lifetime of the meson through that portal. And we have some explicit plots for that. I was checking if I had them in the backup, and I don't. I didn't put backup slides, so I can't show you those plots, but they're in the paper. So this is obviously model dependent. We built some UV completions. Those are, we tried to be, fairly simple. We were trying to make simple ones, but it's bottom up simple model building rather than ultra well motivated top down.
Yeah.
But you're absolutely right. If you've got a given lifetime, right, you can't do anything. Yeah.
All right, other questions? We're just about at an hour. I want to give anyone a chance to ask if they've got anything. All right, fantastic. Well, thank you so much, Jessie, for that talk. It was really interesting and I think really applicable to a lot of things that folks here are doing.
Okay.
Yeah, and I will see you in a second. I'll send you for another Zoom room. All right, bye. Thank you so much.
Thanks again.
Yeah, thanks for the invitation. It was great to talk to you. And thanks for your great questions.